Alrighty, cool. So we all know, Robin already said what this is going to be about. It's going to be V equals IR. We already said, thanks to Sarah, what those were. We have voltage, current, and resistance. My guess is most of you have no idea what those words mean, and that is totally okay. So we're going to start with something that's even simpler than that. Who knows what electricity is? Just in general, right? Shara, what's electricity? The movement of electrons. Fantastic. So we have in our world right now, in addition to all the atoms and molecules and stuff that makes us up, we have a whole bunch of random electrons just kind of flying around. And the cool thing that we discovered many years ago is that we can kind of take these electrons and we can actually control their movement of them to allow us to use them for electricity. And that electricity can then be turned into energy. And that energy can be used to power things like lights and motors and locks and many different things that we use in our everyday society. So a lot of you guys are building these circuits and you're working with all of these different components and you're soldering them in. But if we don't have a really good understanding of what actually allows that electricity to flow and how we control that electricity, it doesn't really mean much. So the words voltage, current, and resistance allow us to kind of have a way to better explain what's actually happening. So what I'm going to do is I'm going to model the electrons. I'm going to pretend they're people for a second. I'm going to pretend that everyone in this room is an electron, right? We're going to shrink the room a ton. We're going to make it about the size between these desks right here. We're going to shove every single one of you inside of there, right? You're not going to be very happy, right? You're going to have, obviously, as young people and as electrons, where you have a lot of energy in you. You got a lot of movement. You're trying to move around. You're trying to, get up out of your chair and kind of run around. And if you're stuck in there, that's a problem, right? You're really going to want to kind of like have a lot of energy in getting out. So if we're in an enclosed room and I open that door, what's going to start happening? A lot of people are going to start leaving, right? So my question is, if I have a bigger door, how is that going to change how many people are coming out? More people, right? So if I make that opening even bigger, when I have that kind of when I have the same number of people in there and the same size, but I open the door a little bit wider, I can get more people flowing out at the same time. So what we would call current is that flow of people or the flow of electrons from one place where they really don't want to be to another place where they kind of do want to be, right? So we can increase what we would call the voltage by doing a couple of different things. In this situation, the voltage is the pressure that you feel as a person to want to leave that system. If I increase the heat and get rid of the air conditioning in that little closet area, are you guys going to be more or less likely to want to leave? More likely, right? So that's one way we can increase the voltage. How else might we be able to increase the voltage in that situation? Yeah. Add more people. That's a great way to do it. How else might we be able to do it? Yeah. So opening up the door more, does that increase the voltage at all? That's the question. So the voltage is just all it is my desire, my motivation to want to leave. That's all the voltage represents, right? So does opening the door change my motivation at all? Not really, no. Shrink the room. That's another great way to do it. You have less space individually. So these are all ways that we can kind of physically model some of this voltage. So voltage really is just the pressure. How bad do you want to leave that system? How bad, if I have a battery that's full of electrons, how bad do those electrons want to leave? So if I have a 9-volt battery versus a 3-volt battery, that's really the difference, right? My 9-volt battery is just saying, it doesn't necessarily mean I have more electrons in there than my other one. That we can model those in different ways. All it's saying is it's really just the pressure. How bad do those electrons want to leave the system that I have for them? That makes sense? Any questions so far? Cool. All right, so next, we're going to go to current. So current, as we said, is really just the movement of people, right? It's the movement of those electrons. And if I increase or decrease the size of that doorway, we can increase or decrease the current, right? So the doorway in this case is a way to kind of resist the flow of people. It's a way for us to say, if I have a doorway that is only allowing one person through that door, it's resisting all of the other people on the other side, right? It only allows one person to go. So let's say I have a tunnel right after that room that's as wide as possible, and I'm letting people out one by one through my door. How fast are people going to move in this regular tunnel, even though the tunnel is huge and I don't really have any resistive elements. I don't have any more doors to go through. It has plenty of room for people to run around. How many people am I going to have individually in that line? Still one, right? It's limited by the resistance I had by the door. It doesn't matter how much room I have after that door. The door is the resistive element that allows me to control exactly what my current is. And a resistor in a circuit works the exact same way. So if I put a single resistor in a circuit, and that resistor is, who knows how you model a resistor, or what the unit of measurement of a resistor is? An ohm, exactly. So the more ohms you have, the more resistance that resistor actually has. So if I put a single resistor into a circuit, it's going to change the entirety of my current for the entire circuit, right? Even though I might not have a resistor over here, that one resistor right there changes the current for the entirety of my circuit, and my current in one place cannot be different than my current in another place. Does that make sense? Cool. All right, so this is the equation that we come up with. Who knows who came up with this equation? Oh, it's Ohm's Law, exactly. So we're modeling this in the same way. Voltage, who knows the units for voltage? Volts, yes. How about I, which is current? Amps, exactly. And R, resistance, we just said, ohms. So these are the three. We have voltage, we have amps, and we have ohms. That's a pretty bad drawing. There. Okay. So this is the what you're going to see as the units for each of these. So now, as we were saying with the door, if I decrease the size of that door, right, I'm going to decrease my resistance, but I'm going to keep the pressure for you guys to leave the exact same. I'm not going to change the pressure that you have to want to leave that room. So this is going to stay the same. So if I decrease my resistance, what's going to happen to my current? It's going to increase, right? So we have inverse proportionality, as we would say, between this current and the resistance. If I have the same exact pressure, if my pressure isn't changing, then and my resistance goes down, then my current is going to go up. It means that I can have more people flying out of that room and into the next tunnelway. And we could do the same thing somewhere else. If I have the same sized door, but I increase the pressure. Now it's a little hard with actual people, but let's say instead I'm going to model it as water, right? So if I have a sink that I'm regulating the flow based on like this here. So this has a certain pressure on the back end. If I regulate the flow here and I leave this here, but I increase the pressure on the other end, what's going to happen to this water? It's going to do what? More is going to flow. Exactly. It's going to increase my current. So in this case, the water flow is represented by the current. This is going to represent my resistance. How resistive is this? What is the resistance that the sink has against that back end pressure? And if I were to increase the pressure, which I'm not capable of doing right here, but if I were capable of doing that, it would increase the flow. Exactly. Anybody have any questions? Cool. So this is the basics of Ohm's Law. It's really just how all of these different elements that you're going to be using, resistors, diodes, transistors, all of these things are going to operate off this basic model and fundamental understanding of how we can use these three main topics to better understand the electronics that are happening in our system. Cool. Nobody has any other questions? Yeah.
When you increase the resistance, how does that affect the other thing?
Yeah, so if you increase the resistance and you were to keep the voltage the same, what's going to happen to your current? Decrease, exactly. So think about what the door again. If I have the same amount of pressure, but I increase the resistance by changing the door to be smaller, I can let less people. Exactly. Yeah.
This is very central to all of your projects. All of your projects are going to have voltage or current running through them.
It is super, super important for you guys to actually understand this. So if there's trust me, if you're not totally sure with all of this, and if they're like, I don't really know what happens with voltage when I do this, and I'm not really sure about that, then let me know right now. Cool. All right. So the next part of this is actually looking at it in a circuit. So if I have a 5-volt battery, I'm going to represent any battery that you're going to see. It might be shown like this. It might be shown like this. We're going to show it like this for now. And then in addition, there might be something that you'll see. It can either be shown like this, or it might be shown like this. So this is going to represent something we'll call ground. Who knows what ground is? Yeah.
Sort of where like you direct the current to there and it sort of disperses the electron.
So yes and no. In a system where like you're plugging AC power in, so like a wall outlet, that is what ground's used for. But ground as kind of like a normal understanding of what ground in the circuit is it's really just a reference point. So if I were to jump off of a 10-story building, right? How many stories am I going to fall? 10. What if I said that the bottom 4 stories were below the ground? How many stories am I now going to fall? 6, right? So just because I'm jumping off that 10-story building doesn't mean I'm falling 10 stories if my ground, my reference point for those 10 stories wasn't actually at 0. So all ground does is it provides a reference point for the amount of pressure that we actually have to do something. So in this case, my battery is going to have, let's say this is a 9-volt battery, right? So I'm going to have positive 9 volts at the top of here, and then it's going to be 0 volts at the bottom, or my reference voltage for where it is. And I'm going to connect that to ground in my circuit. I'm just going to kind of label it as ground. It's going to be the same reference point for the rest of my circuit. So in this case, I have 9 volts between here, and then I have another 9 volts between here. So in this case, I have 3 kilo ohm circuit here, or we'll call it a 3 ohm circuit, or a 3 ohm resistor. You're not really going to see this because it's a pretty high amperage, but just to make the math a little bit easier. So I have 2 resistors. We're going to call these resistors in series. So when 2 resistors are in series, that just means that they are attached together where the full voltage across both of them combined. Something else that you might see them in would be parallel, in which case they actually share the voltage. They are each voltage source here. So if I have this at 9 volts, this would be at 0 volts, and it shares the 2 of them. So I don't necessarily need to go into the math between the 2, but the point is that you can actually use this V equals IR to better understand what's happening at the different points in your system here. So because it's fully proportional, right? I know my voltage, my 9 volts, using my reference voltage of 0 here, is across my 2 resistors. Now in series, my resistors add, right? So they're just going to add up together. So what's my full resistance of my 3 ohm and my 6 ohm? 9 ohm. Exactly. So this is equivalent to a 9 ohm. Now, if I know the full voltage across here, and I know my full resistance across here, I can figure out my current. So if I have a full voltage of 9 volts and a full resistance of 9 ohms, what's my current going to be? Just 1, right? It's going to be a single ohm. So I know that in this whole circuit, just as we said, your resistance will change the current for the entirety of your circuit. It doesn't just change it for one little part, it changes it for the whole loop of your circuit. So in this case, I have 1 full amp running through this circuit. Now, this is where it gets fun. I can take this 1 amp, and I know the resistance across each of these. So if I have 3 ohms as this resistor, and I have 1 amp running through it, using this, what's the voltage across that resistor? 3, exactly. So I know that my reference here is I have 3 volts here across this resistor, right? It doesn't mean that this is at 3 volts and that this is at 0. It just means that between these 2, I have 3 volts. Now, how about this 6 one? So if I have 6 ohms and I still have my 1 amp, what's my voltage going to be? 6, exactly. So I'm now going to have 6 volts across here, and I'm going to have 0 volts here. Again, in reference. Now, we used this ground to show that full reference point for the whole entire circuit. So I have 0 volts here because this is grounded. So if I have 0 volts here and I have 6 volts here, what's 6 minus 0? 6. So this is going to actually stay at a full 6 volts. But this is where it gets a little different, right? Because this is no longer at 0. We've decided that this point, any point where you have just a wire and there's nothing else but the wire, if I have no change in resistance, right, and my current isn't changing, then the pressure that I have on any of those electrons to move stays the exact same. So if this is at 6 volts, then this is at 6 volts. So I'm going to change this. And I know the difference between this point and this point was 3. So what's 6 plus 3 then? 9, exactly. So I have 9 here, which matches up perfectly to the fact that I still have this one wire that's all the same, where the pressure is all the same, and I had 9 volts on top of this battery. So that actually makes perfect sense, and the math worked out exactly as it was supposed to. Does this make sense to people? Anybody have any confusion? Yeah, what's up?
Less confusion and more of a question. Doesn't technically wire also have a resistance value to it?
Yes. So these are ideal wires in this sense. In a lot of the things you are doing with the size of the wires you will have, the resistance, you can pretty much think about it as negligible, but you are absolutely correct in the sense that wires will have a, in this case, actually it would matter because these are relatively small resistor values, but it might have a resistance of like 2 milliohms or something, whereas like doing the full math would just make more sense not to worry about it, but you're not wrong at all. That's absolutely correct. Yes?
What does the ground mean on a breadboard?
Yeah, so the ground on a breadboard. So if you guys will look at a breadboard, I don't know if we have one sitting around here, but there's like 2 rails on the side, and one is negative, one is positive. So the ground is not any different than any of the other things. The only thing is it is useful for you when you're figuring out that reference point. If you have a whole bunch of components and you want this reference to be the exact same, like if I were to have one that was referenced here and one that was referenced here, it'd be the same as that building thing, right? Where like some would actually be on the ground, some would have a couple floors below the ground. You want to make sure that everything has the same ground level so that you can know exactly how much above that ground level everything else is. So what that ground on a breadboard does is it allows you to have a full rail where you can plug every ground wire into the same exact ground so that you're sharing the same reference point for all of your circuits. Does that make sense? Cool. Anything else? Again, super important for you guys to actually understand this. Take all the time you need to come up with questions. Nothing? Yes.
For the equation, I didn't really get it. Like, if you increase the voltage, how does that affect the IR part?
Yes. So if you increase the voltage, let's say I increase the voltage but keep my resistance the same, right? So if I increase this voltage and like I'm going to increase the pressure, trying to make you leave the system, but the resistance for you leaving that system does not change, you're going to have more movement because of that pressure change, right? So in the case of the sink, right? If I kept this at the same place but increased the pressure on the other end or the voltage, it would make more water flow or it would increase my current. And you could do the same thing. You could say if my current is the same, if I have a source that can only pump current at a certain rate, right? Like if I only have 20 people in there, the maximum I could do is 20 people, right? So if I have something like, I guess that's not a perfect analogy, but let's say I can only pump 20 people at a time. There's no way I can change it, but I have a constant rate of 20 people. Then increasing my voltage would increase the resistance instead, if that makes sense. Cool. Anybody else? You sure? Yeah.
I didn't get what you said about the ground thing for a breadboard.
Sure. So pretty much with a breadboard, you just have a whole bunch of like rails that are connected to each other, right? And so most of them are horizontal, as you guys will find out. There are 2 on each side that are vertical. And so one is labeled negative and one is labeled positive. And the one that's labeled negative is usually the one that we use as the ground. So there's nothing special about it on the breadboard. The only thing is it's a nice thing for you to use as that ground reference point because you want to make sure that all of your circuits have that same ground, right? So if you have one ground from, like, let's say your Arduino has a ground, right? If I plug that ground into that, now my entire rail is using the same, just like this, it's using the same wire, right? The pressure difference at that exact point is no different anywhere on that line. So you can then use that as a reference point for all your other circuits that you're doing. You have an ultrasonic sensor in there that needs ground. You throw it on the same rail. You have a couple of resistors that are also attached to ground. You can throw it on the same rail. Does that make sense or still confusing?
So still a little confusing, but can you only do it like once or do you have to do it multiple times?
So you can, if you do it one time, like if you put a single ground there, the entire rail is ground, and you can use it as many times as you want, as many pins as it has. That being said, that there are 2 on the side, usually you would need to connect one to the other to make them both ground. Yeah.
So when you use the ground, like on the breadboard or whatever, is that like you're defining that as 0, or like you're finding the value of that and like.
So in that case, you are personally defining it as 0. You're saying this is my 0. This is where I'm going to tell every other part of my circuit this is where my ground level is. Whatever your voltage is now going to be in reference to this being my ground.
Okay.
We good? Cool. All right. Definitely ask people if you're not comfortable with this, because you got to know this right out the gate. It's going to help you a lot with debugging and trying to figure out what some of your problems are. So
This will be on the YouTube channel too. So relive this moment.